We're almost ready to get started. If you're here and physically in the room, welcome back. Please do the attendance thing on Top Hat, so I know physically who is here today. If you're joining us by Zoom, welcome. Please do not do the Top Hat attendance thing. Not that you can see it anyway. Although if you bring up your Top Hat, you probably can see it. All right. Does anybody need any more time to do attendance? 2, 4, 6, 8, 10, 12, 14, 16, 18, 20. There's way more people in the room than have answered yet. So I'm going to give you a couple more minutes to do this. So as you're coming in, do your Top Hat attendance thing. I'll leave this up for another minute. Very weird semester has gotten underway. How did the first lab week go? I guess half of you were in lab and half of you were not in lab. Is that how it's going to work in optics lab? Okay, well, that's weird too. We'll figure it all out as we go along though. I did an office hours this morning that I think worked reasonably well. There was a Zoom, at least 3 or 4 people showed up. So I think it worked reasonably well. Again, the way office hour, I'll have another office hour session tomorrow morning at 9:30 to 11:30. I don't mind. It's not horrible if you actually come to my office. Just what used to be a gathering point for lots of people to come in and work on problems no longer is that. But what I have done is make that sort of happen on Zoom. I have breakout rooms, and I'll put everybody who comes to my office hours from this class into a breakout room. I'll pop in and answer questions, but you guys can work together, which is kind of one of the points of office hours as well, getting together and asking each other questions and helping each other out. So hopefully that's a model that will work moving forward, but we'll, you know, it's all an experiment. We'll see how it goes. Okay, let's get right to it. So I think I just need to share my desktop. I'm going to close out the attendance, 27, sure, why not? This can go away. And I think I'm going to be fairly much here most of the time. Okay, so the first homework assignment, as you know now, is a review of Analytical Physics 2. And that leads us right into our first topic. So I'm going to kind of go over some Analytical Physics 2 topics, and we'll see how that works. Now, last time I did this, I closed this out and you couldn't see me anymore. So maybe I just want this. And maybe I actually want to just pin this. How do I do that? Pin video. There we go. Now you can see me. I'll put myself off in a corner here. And this is going to be my whiteboard. Again, it's a very small whiteboard. I don't have much room here. I'm going to be doing a lot of stuff today. If you need me to go back and either people in the room or people on Zoom, let me know. I'll go back and change it. So we're going to start off with figuring out how the pens work. Yep. Yep, that's what I want. A black pen. Cool. Am I not plugged in here? I think I'm plugged in here. Okay, that's working now. And that's working now. Okay, great. Let's start with a, what? Oh, I see what I did. I turned it to eraser and then I didn't turn it back. Okay, hopefully this is working now. Yay, it's working. Okay, let's start with a review of waves. Okay, so I'm gonna write down an equation that should look somewhat familiar to you. Y equals y sub m times sine of kx minus omega t. This is a omega, not a w, plus, let's say, phi naught. Or you could also write this same parentheses, same thing before the parentheses, but inside the parentheses, you might also write k x minus x naught minus omega t. These are two ways of saying the same thing. And this is a typical way you would write a propagating wave. So there are terms in here that are associated with the x position. What are we actually talking about here? Let's think about what this is. This might be a wave on a string, right? And it might be that in fact it is, that the wave is propagating in the x direction, and that at a given time it might look like that, and that the y direction is in this direction, and that's telling you the position of that location of the string as a function of time and also as a function of x, right? So what is omega? Got this equation. What's this omega? I said that was an omega, not a w. It's a Greek letter omega. What's omega? Yep. Say it again. Phase difference. Excellent guess. That's not what it is, though. There is a phase difference up here, but it's not omega. Go ahead. It's an angular frequency. If you probably came, and I think I've never taught Analyt II or Analyt 1, and I'm not even sure which car set's covered in, but my understanding is that you used F instead of omega. Is that right? F is just a normal frequency. That's right. F and omega are similar. They're both frequencies, but there are differences between F and omega. And it's important to understand what those differences are and how they work. So you are exactly right, in fact. Omega is the angular frequency. It is similar to the F, if you used F before, is the cycle frequency. It doesn't even, we could write these terms in terms of F if we wanted to, but we have not, we've written them in terms of omega. These even have different units, kind of. The units on omega are radians per second. The units on F are cycles per second. Of course, there are how many radians in a cycle? A cycle is a full progression through the wave one time. How many radians are there in one cycle? 2 pi. So F and omega are related by 2 pi. In fact, omega equals 2 pi times F. Okay, great. This is going to be really annoying if I can't scroll up here. Maybe I'll bring the other one next time. Okay, there's some other terms in here that we might be interested in that we may not know what they are. So what is this phi naught term? That is the phase shift. That is, yeah, phase constant. It is how much, it's not changing omega, the frequency, is changing how fast those waves come. Changing phi naught is just changing where they physically are located in space at any given time. It's just a fudge offset to shift the wave one way or another. And the same thing with x naught. This does exactly the same thing as the other as phi naught. It shifts the wave in omega's case, in phi's case in angle space, and in x naught's case in physical x space. They have physical different units, but they are fundamentally the same kind of thing. So phi naught, these are phase shift. Phi naught and x naught are phase shift parameters. Phi naught is an angle. X naught is in physical space. And they're related to each other. They're very unimportant, as it turns out, though. Wavelength is important, frequency is important, phase shift almost never is important for anything practical that we're doing. How about K? What's K? It's a wave number. It is related to a parameter that we'll call lambda, which we define to be the wavelength. The wavelength is physically how far it is from one peak in the wave to another peak on the wave, or one trough on the wave to another trough on the wave. That's an easy thing to visualize. Wave number is not as easy to visualize, but it's easy to calculate if you know what the wavelength is. You can just take 2 pi over it. They're inversely related, though. The bigger the wavelength, the smaller the wave number, and vice versa. Light, for example, this is all going to be leading up to the first sort of unit of the class, which is electromagnetic waves, light waves. Light waves are going to have very small wavelengths, most of them, at least the ones that we can see, and that means very large wave numbers, like extremely large wave numbers. Okay. We can also talk about wave speeds. How fast are these waves propagating? The velocity of this wave is, you can determine if you've determined all of the variables we've written down so far. For instance, if you know the frequency and the wavelength, it's just the product of those two variables. This is in physical cycle frequency and physical wavelength. If you prefer angular frequency and wave number, you can do that too. The factor of 2 pi's cancel out, and it works out fairly nicely. Okay, again, we're going to be applying these to light. And the cool thing about light is this wave speed, at least in a vacuum, is always constant. So for normal waves, you can vary all 3 of these parameters. You can change the frequency, you can change the wavelength, and you can change the wave speed. For light, you really only have, well, that's not true. You can't change all 3. You can set any 2, and setting those 2 will set the 3rd one. For light, you really only have one choice. The wave speed is set. Setting the frequency, therefore, automatically sets the wavelength. You only have one real free parameter when you're talking about light waves. For light, velocity is equal to the speed of light, which is why we call it the speed of light. We usually designated c. And that is a constant in a vacuum. Interestingly, it's not constant, not in a vacuum. That's a detail we'll get to later on. In fact, I'll get to it right now. Look at that, it's the next thing in my notes. Is next week's lab, are you doing, I almost always teach optics lab, but I'm not this semester and I don't know how they've changed it. Are you doing next week the index of refraction lab? Thin lenses? What? 2 weeks from now. Okay. What are you doing next week? Oh, they're all 2 week, they're all kind of, no, they're not all 2 week labs. You're just doing half and, yeah. You know what next week is? Anybody remember what next week's lab is? What's that? Oh, right. Because Monday's Labor Day. Right. The next lab you do will be the index of refraction lab. Okay. The index of refraction of a material is defined to be how much slower light moves in that material than it does in a vacuum. So C over V. So N is index of refraction. We're not going to do anything with this right now. We'll come back to it later. But I thought I'd mention it since we're talking about wave speeds. C is the speed of light in a vacuum. V is the speed of light in the medium, whatever substance you're talking about. Okay, cool. And this has properties. What N is will depend on how much light is refracted through that material and determine how good a lens you can actually build. Okay, one last point on this point of waves before we move on to Analyt II is there's an interesting thing here in the sign, which is there's a negative sign in front of this omega. Why is there a negative sign in front of that omega? That's an important negative sign. And it's important to think about why that negative sign is there. I will say, this is the equation for a wave that is propagating in the positive x direction. So at some time in the future, this wave will be moving slightly in this direction. I'll even draw a little arrow there. Why is there a negative sign here in front of this omega t term? Yeah, there's some kind of interesting mathematics going on here. You're probably on it. There's a more intuitive way to think about it, though. Can anybody put it in a more intuitive way? Yeah. Say it again. When you're subtracting the angle gets, say it again? Right. Right. This is what I want you to think about. Why is that negative sign there? Let's think about that. There's two ways really to draw this wave in a snapshot, right? You could say, here is the wave at t equals 0. Here's a snapshot of the wave, right? And that's what I've drawn here. I've drawn what the wave looks like at t equals 0. Let's even put our 0 point here. This is a sine curve, so it might be that this is our 0 point, right? That might be x equals 0. At t equals 0, you've got a normal sine wave here. Let's say I've drawn this such that maybe phi naught is 0, so that we're right here. Let's ignore phi naught for a minute and just think about these two terms. At phi naught equals 0, if I stop this at t equals 0, I've just got a sine x term. It's just sine. So that makes sense. There's a positive x there. It looks like a sine curve. It goes positive in the plus x direction. But what if I, instead of setting time to be 0, what if I instead set x equal to 0 and propagate time through. What happens then? Well, the wave is moving in this direction. We've already experienced this part of the wave gone through, right? What's the next part of the wave that we're going to experience at x equals 0, at t equals a little bit past 0? We're going to experience this part of the wave next. And then we're going to experience this part of the wave as those pieces of the wave go through. So if you think about plotting this same plot as at x equals 0 as a function of time, it looks exactly the opposite. A little bit positive t in time, you're actually going to be traversing the negative part of this wave. And so in spatial sense, it looks like a normal sine curve, but as the wave propagates in the positive x direction, you're going to be experiencing the wave going in the opposite direction. And that's what that negative sign does. Okay. So don't be weirded out by it. It's just there to do the positive x direction stuff. Okay. Great. So we talked about, we're doing this with light. The wavelength of visible light is about 500 nanometers, or if you like, 0.5 micrometers. This is the middle of the visible part of the spectrum. Electromagnetic waves, light waves, can have any wavelength from, I don't know, single nanometers and even smaller to many meters, tens of meters, hundreds of meters, thousands of meters. But our eyes are only sensitive to a small subset of those wavelengths. And 500 nanometers is right in the visible. It's a pretty small subset of the wavelengths that our eyes are actually visible to. And 500 nanometers is right about in the middle of it. So what is the frequency of that wave? Frequency of that wave, again, we can use our formula up here. C equals F times wavelength to determine what F is. F is just C over lambda. If you multiply the speed of light, which is 3 times 10 to the 8 meters per second, and divide that by 500 nanometers, you get something like 6 times 10 to the 14 hertz. And if you like prefixes, 1600 terahertz. This is extremely fast, right? So what is the frequency? That's the cyclic frequency. That's how many waves, crests, pass by every second. So a green photon, a green particle of light, green wave of light that's entering your eye from the fluorescent lamps up above us are vibrating, oscillating up and down 10 to the 14 times per second. More than 10 to the 14 times per second. They get to be pretty staggering numbers. Okay, that's enough of that. Let's move on to something else. This is not as functional as I would like it. Okay, that's wave reviews. How about EMM review? You're doing that on the homework this week. Let's go ahead and do some EMM review because 1, it's been a long summer. 2, you did probably the second half of at least Analyt II in some weird online way. And 3, it's going to be important for understanding how electromagnetic waves work if we understand remember how electricity and magnetism stuff works. So I have prepared and posted on Canvas a PDF file called The Greatest Hits of Analytical Physics 2. And here it is. It has certainly not everything you covered in class last year, but it does have highlights of the things that we're going to be doing with light this semester. You've got forces on charges due to fields, both electric and magnetic fields, and how those are related. You've got describing potentials and E fields related to potentials. probably in ways you haven't seen. You use these equations, but these are probably written in ways that you haven't seen them before. You probably didn't use the del operator, for instance, on the v vector, because you probably haven't even encountered the del operator yet, but that's okay. We're not even going to be using that this semester. Creation of fields by charges, you probably did use. And then you've got these 4 boxed equations, which are going to be extremely important for what we're going to be doing in the next couple of weeks. These are Maxwell's equations. These even probably look somewhat different than you used them last semester, and that's okay. I'm here to try to bridge the gap between what you did last semester and what you did this semester, and also point you ahead to what you're going to be doing in the future. This is the integral forms of these equations. Show of hands if you're in differential equations or have already taken differential equations. Show of hands if you're not in differential equations and have not yet taken it. Okay, you'll probably get there next semester, but the differential forms of these equations are actually much more useful than the integral forms of these equations. You can do a lot more with them. Most of you haven't gotten there yet, so we're not going to bother with that this semester. But just know that this is the integral. There are other ways to write these things that are even more potentially useful down the road. But that's an E&M class for another day. Let's not get there today. You probably remember and recognize things like Gauss's law. Let me pull this out. So this is an extremely useful and powerful equation, Gauss's law. You probably spent at least a couple of weeks last semester working on Gauss's law problems and figuring out how you could determine how much charge there was in an area by what the electric field looked like, and conversely, figure out what the electric field is in a particular place by determining how much charge there was in a particular location. You're certainly going to be doing examples like that on the homework. This is where I'd love to have 2 projectors going, but we can just make it work. You probably didn't get to Gauss's law for magnetic fields. Does that look familiar? It's entirely analogous to Gauss's law. So let's think about Gauss's law for electric fields. So again, how does this work? You have some distribution of point charges and you enclose them in a 3-dimensional surface, 3-dimensional shape. You integrate over that shape the electric field at any given point along the surface of that shape times the surface area vector, dot product of those two. This is an extremely complicated thing unless you do it right. And then integrate that over the whole surface. That is equal to 1 over epsilon naught times the charge enclosed. There is an entirely analogous law for magnetic fields. For magnetic fields, you have exactly the same thing. Have some surface enclosed by closing some volume, and you can determine how many point charges of magnetism there are inside that object. Now, the difference between electric point charges and magnetic point charges is that one of them exists and one of them doesn't. There is such a thing as electric point charges. You can have positive charge things and you can have negative charge things. There is no such thing that we know of yet as a magnetic monopole, a north particle, magnetic particle that only spews north magnetic fields, or a south magnetic field that only is the recipient of those north fields. There is no equivalent. Interestingly, the standard model of particle physics does not preclude that. It's allowed. We have never found one, but it doesn't mean they don't exist somewhere in the universe, interestingly. But since we've never found one, the right-hand side of that equation is 0. Because we've never encountered something that would give us a non-zero term on that side of the equation. Otherwise, those 2 equations are exactly the same. If there were no such thing as protons and electrons, the right-hand side equation of Gauss's law would also be 0. What does this look like in practice? It looks like this. So here is Gauss's law for magnetic fields. Again, what does this practically mean? Well, here is a bar magnet. We need to generate some sort of magnetic field so we can evaluate this. Here's a bar magnet with a north magnetic pole and a south magnetic pole. It doesn't matter what surface we draw, and you're supposed to think of these as a three-dimensional surface on a two-dimensional plane. It doesn't matter what we draw. The number of field lines that come into the surface is always going to be equal to the number of field lines that come out of the surface. Doesn't matter where you draw it, doesn't matter how you draw it, doesn't matter what configuration or orientation you put it in. The integral over this entire surface has to be 0 because whatever field lines come in and give you a net positive in one side, you have to get a net negative on the other side when they come out. And the integral over the entire surface will be 0. So that's Gauss's law for magnetic fields. Whatever field comes into your area, your volume, also has to leave your volume. There is no such thing as a magnetic monopole. There's no point source magnetic field particles. Okay, let's go back to our, there's some other equations down here that are interesting. We're gonna spend most of our time in the next couple of weeks talking about these two equations. There's a Biot-Savart down, we're not gonna deal with this one this semester. This is interesting, and there's some wave equations that I just talked about. These two, though, are going to be useful for next week's homework. These are energy densities of fields, right? If you ever thought about electric fields and magnetic fields being not anything really all that real, just useful for calculating problems and forces between two particles, this should disavow you of that. There is energy associated with an electric field. There's energy associated with the magnetic field. Physical, actual energy that you can measure. And if you want to know how much that is, well, actually, we've got those terms here. The energy density of an electric field is 1/2 epsilon naught times the strength of the electric field in that location squared. And there's almost an analogous, completely analogous thing for a magnetic field, 1/2, 1/mu0 times the strength of the magnetic field squared. So there is physical energy associated with these fields. They are real and tangible in some measurable way, besides just point particles. It's all very weird though, right? Action at a distance is always kind of spooky. Okay, great. So let's go to Faraday's law of induction. This is Faraday's law. You probably didn't see Faraday's law in this particular form last semester. You probably talked about Faraday's law in terms of if you've got a changing magnetic field, you can induce some current in some wire, right? You've got a loop of wire and you have a magnetic field running through it, and you change the magnitude of the electric field, magnetic field, you can induce a little current in that wire. It's more general law than that. And in fact, even if you didn't have a loop of wire there, changing the magnetic field in an area will create an electric field. If you have a wire there, that electric field will induce an EMF current and you'll get a little current going. But even if you don't have a current there, a circuit there, you can generate that electric field. And this is the more general way to think about that. It's very analogous to Gauss's law, right? You have the dot product of the electric field. In this case, it's not a surface integral, it's a loop integral. You're just going around some loop, some two-dimensional surface, ds. That dot product, take the integral over the entire loop, is equal to the negative of the change in the magnetic flux per unit time as a function of time. Okay. So this is different than any E field you've probably even thought about before. Let's actually take a look at what this looks like. So here is, how would you generate a uniform magnetic field? Well, one way is a solenoid, right? If you take a loop of electric current and a wire, and you twist that wire around, you get a magnetic field propagating through the loop. If you loop that a bunch of times, you can get a fairly uniform magnetic field inside that loop. Here's an example of that, right? So if you take that and you change the current in there by some amount, you're going to be changing the electric magnetic field, and that's going to be changing the magnetic flux, and that's going to introduce some electric field inside that area, right? You're going to get some weird. You've always thought about electric fields diverging from positive charges and converging into negative charges. This is a completely different thing, where you have a loop of an electric field, very analogous to what looks like usually you see loops of magnetic fields. So this is what those things kind of look like, right? You've got circular path, and these are the electric field lines. If you change that, as you change the current in the wire and change the B field, that will induce electric fields inside the solenoid itself. And you get these weird looped magnetic field lines. Now, if you're paying attention and thinking about this carefully, you're going to ask the question, how does the electric potential work for looped electric field lines? And it's complicated. I don't want to get into it, but it's a good thing that you're asking the question, and you'll learn more about it later. So let's just try this out, though. Let's actually use this equation to make some calculations. So our equation is, let's just do a solenoid. Let's say our solenoid has, I don't know, 50 turns. Let's say the current is 4 amps. What is the magnetic field inside the solenoid with 50 turns and 4 amps? You might remember from last year that the B field associated with this is mu naught times the current times the number of loops. And in this case, that turns out to be about 25 millitesla. What is the E field associated with this magnetic field solenoid setup? Yeah, mu naught is just a constant. Yeah, it's the permeability of free space. And it really, you know, how should you think about it? It really is this. It takes normal things and turns them into magnetic field strengths. That's really, it's the constant that gives you magnetic field strength. I don't remember. Was that? -7, something like that. Look it up. You don't ever have to memorize the name of a constant. It's always look upable. That's okay. That's quite all right. But the question is, what's the E field? Let's go back to this equation. So we've got some magnetic field. What is the E field associated with? Certainly there's some magnetic flux. What is the E field associated with the magnetic flux in this particular case? We have a constant magnetic field of 4 or 25 millitesla. That's exactly right. This is not just the magnetic flux. It's d magnetic flux dt. It's the change in the magnetic flux that matter. If we're not changing that magnetic field, we're not changing that magnetic flux, we get 0 E field. We have to actually physically vary the magnetic field in order to get an induced electric field. And so in this particular case, before we start changing the current in the solenoid, there is no electric field. It is 0. since dB dt is 0. We aren't actually changing anything. Okay. Now let's actually change the current in the wires, which will actually change the magnetic field. If we drop the current to 0, let's say over 5 seconds. So as the current through the solenoid goes to 0, the magnetic field that it induces will also go to 0. And now we do have a change in magnetic field, and we should get an induced E field. So B is going to go to 0. Now, what is phi sub B? This is the magnetic flux. If you were to put a definition on this, this really is B dot dA, or the integral, I should say, of B dot dA. That's really what the magnetic flux is. Again, if you've got some solenoid and you're moving the B field, A is in that direction and B is in that direction, this simplifies a lot, right? We almost always want to set these geometries up so that we don't have to worry too much about dot products and cosines, and so that things in our integral are constant, and the integral is really easy. That's certainly what we've done for ourselves this time. Magnetic flux in this case is pretty simple because, well, the B field is always perpendicular to always parallel to our A area vector. So that dot product really becomes a regular product, and we can just think about the magnitudes of the B fields. So since these are parallel, the dot product of vectors just becomes a product of the magnitudes of those vectors, and we can just say integral of B times dA, since B is parallel, or I wrote perpendicular, but I meant parallel. Since B is parallel to A. And we know that inside of a solenoid, the magnetic field itself is pretty uniform. It doesn't vary over that area integral. And so we can pull it out of the integral, right? This is just B times the integral of dA. The integral of dA is just A. And the area of our circle that we've drawn in there is pi r squared. So this becomes, the magnetic flux can be a really complicated thing, but if we set our geometry up right, it should be a fairly simple thing, which is really just the magnitude of the magnetic field times the area of the thing that we've drawn. If you start moving things in weird directions or changing the B fields, it becomes a lot more complicated, but we're not going to deal with those situations. Okay, so man, I wish we could see more of this stuff. Really, we want, let's go back to our equations, right? It's the negative of the magnetic flux derivative, time derivative of the magnetic flux. So d B times pi r squared dt is just pi and r squared are constants. This is dB dt. This is the right-hand side of our equation, right? And what is B? Well, we know what B is. We defined B up above to be mu naught times I times N. So this is really there we go, pi r squared times d of mu naught times I times N, which is what our B is, dt. Mu naught is a constant, N is a constant. The only thing that's changing in there is I. This is really pi r squared times mu naught times N times di dt. The entire right-hand side of that equation. And the left-hand side of the equation is pretty simple. It's a loop integral of E dot ds. Let's go back to our picture. Our loop, the loop that we've drawn just has radius r. And we hope that the magnetic field or the electric field is going to be constant at a given distance from the origin. And we hope that that electric field is going to be always parallel to the loop that we've drawn. And so the dot product then becomes a regular product, and we can pull the electric field out of the integral because it's constant, and the left-hand side becomes a very simple thing to do also. This just is a loop integral of E times ds, since they're always parallel. And that is just E times the integral of ds. And that's just E times the circumference of that circle, which is 2 pi r. And that's the left-hand side. And that whole thing, that whole thing has to be equal to each other. So we've got E times 2 pi r on the left, and we've got this pi r squared mu naught n di dt on the right. And now we know everything that we need. We know what r is, we know what mu naught is, we know what n is. Di dt we've defined. We're dropping it from 4 amps to 0 amps over 5 seconds. That gives us a di dt. We can plug in and find what the electric field is at that point. I'm not going to bother to plug in the numbers. You can do that on your own, but there we go. So if there's a coil inside there, you'll get a current, right? Even if there isn't a coil, though, you'll get some E field, and its strength will depend on the position. If you solve this for E, you're going to notice that there's one of these R's cancel out with one of these R's. The pi's cancel out. Let's just solve this. You get R over 2 mu naught n di dt, right? What is the electric field, induced electric field, going to be at the very center of our solenoid? 0. R is 0. The intuitive way to think about that is if you make your loop smaller and smaller, the magnetic flux gets smaller and smaller and smaller, and eventually goes to 0 as R goes to 0, because your magnetic flux goes to 0 at the center. Okay, good. Cool. How much time do I have? 2 minutes left. Great. The next thing I want to talk about is this equation over here. You might recognize this as Ampere's law with an addition attached to it, right? Ampere's law tells you what the magnetic field is around a current carrying wire. You've got some current going through a wire. You can tell what the magnetic field will be around that wire, the induced magnetic field from that current. But it turns out there's a second part to Ampere's law. It's specifically Maxwell's induction law, which says you don't even need a actual current, charged particles moving through space, to generate a magnetic field. In fact, it's completely analogous to Faraday's law, right? If you have a changing electric flux, an electric flux whose magnitude is changing over time, that will induce a magnetic field. It works exactly analogous to Faraday's law. So we'll explore that possibilities and do an example that looks exactly the same as the example we just did, except you're swapping the electric field for the magnetic field and the magnetic field for the electric field. Other than that, they look entirely analogous. All right, we'll do that example next time. I have Office hours again tomorrow morning. Don't forget about that. Homework 1 is due Friday at 5 p.m. Homework 2 will be up sometime Friday afternoon, probably. See you Friday.
So you were saying that like we can just do this by ourselves. I was wondering like how would you like this section? You were saying that it goes from
DIDT? Yeah. So it's a constant, right? DIDT is, if you change the current linearly, it is really delta I over delta T if you're doing it in a constant way. So I can say delta I is negative 4 amps. Delta T is 5 seconds. Just take your delta I and divide it by your delta T. Since it's a straight line.
That's what I thought.
Yep.
I think to get more complicated.
Nope, that's all it is.
Thank you.
You're welcome. See you Friday.